Okay, as soon as it's readable, if there is something that the audience could not see, please let me know and I will zoom it. So thanks on for the introduction. So thanks for organizing the amazing ASAP seminar. So today I will be talking about our paper on linear attention for bidirectional sequence modeling. Probably you have heard about for sure you all know about like linear transformers, SSMs, Mamba, DeltaNet, and so on and so forth. On here, we are just more working and investing them on bidirectional tasks such as image classification, masked language modeling, and so on and so forth. So, let's get started. So basically, the main motivation is that not all the sequences are causal, meaning that actually, indeed, maybe I can claim most of the sequences around us are not causal and are bidirectional, meaning that like we have a full sequence and we have access to the full sequence during training and during inference as well. For example, DNA modeling, image classification, and as another popular topic these days, diffusion language models, which you have the full sequence of tokens. And then either you want to predict something or you want to generate something based on this badge of full sequence. And the perfect examples are very applied tasks. And actually, it has been even promoted more and more, and several different applications are relying on bidirectional sequence modeling. So many models have been adapted to bidirectional tasks. The most of them is transformers, which we have like very early after introduction of vanilla transformer, which actually vanilla transformer in its core, which has an encoder which is bidirectional. Several other variants also have been applied as a bidirectional variants of transformers. One of the most famous ones is VIT, which is vision transformer, that you apply basically a transformer encoder into the image patches. You tokenize your image as patches, and then you pass it to the vision transformer, and then detect, for example, do image classification task. Or like several variants that have been on top of VIT, such as Dino V2, Clips, and so on and so forth. Another task is like masked language modeling, which like you have a full sequence of tokens and part of it is masked, and the goal is to demask the unmasked part and basically predict what is missing in between. And another very famous applications again these days is language diffusion models, which again, it's the same as masked language modeling, but you do it in a very naively. I'm like just describing it. You do it in multiple steps, like from pure noise, you try to generate the full sentence such that it's not like in a paradigm of autoregressive and one next token prediction. You try to predict the full sentence and by denoising it from the full noise. And also in context of linear transformers, several different models have been adapted to bidirectional sequence modeling, such as Vision Mamba, Hydra, Lyra, for different applications of DNA modeling, images, and also Hydra, which is the official Mamba 2's extension to bidirectional sequence modeling. So basically, we have so many models that in linear transformer domain and SSMs and full transformers, softmax transformers that are applied to bidirectional sequence modeling. So that's the motivation and why we want to study these tasks. So let's get a little bit back into what are the main basics and what are some transformer SSM trade-offs, which one can see also in the causal sequence modeling or autoregressive next token prediction or autoregressive formats. So one of the main ones is like that transformers are usually faster in speed, specifically for short sequences, because they use the attention, which is full parallel form. And but they are in inference. In inference, they are quadratic. I mean, they are linear, or with kernels they can be considered as linear, but still they need to access to all the past sequence of tokens in order to predict the next one, which makes them inefficient. On the other hand, SSMs or linear transformer are having a very nice property that they can be presented as an RNN. So they have a very nice inference efficiency. Basically, they don't need to save any of the previous tokens and they just need to update their hidden states. But on the downside, their training speed falls shorter compared to transformers. And actually, this has been also studied relatively decent amount in the field. One of the good examples is from the GLA paper, which actually you can see that for the causal sequence modeling, the training throughput of transformer for relatively short sequence of 2K is significantly higher than Mamba, like around twice. Also compared to GLA, still it's higher, like by a little bit of a margin. So also another thing is like that, is this same applies to bidirectional tasks? And the answer is actually yes. If you train VIT, these are actually from our paper, that if you train VIT, you can actually see that the training time of VIT and DIT, which are vision transformers, is roughly twice less than SSM variants like Hydra and Vision Mamba. And the reason that Vision Mamba probably, I mean, not probably, the Vision Mamba is slower is like because it's using only on scans for training, while Hydra, being based on Mamba 2, is using the chunk-wise form, which is faster significantly. And basically, the chunk-wise form of Mamba 2 was named like SSD, which all you're familiar with, and Hydra is applying 2 SSDs on the reference on different directions in order to train, and then during the inference, you can have choices between different representations based on your hardware resources. And as you all know, like Flash linear attention is a very good library that like applies this chunk-wise algorithm for so many different variants like DeltaNet, gated DeltaNet, GLA, and so on and so forth. So why do we want to do bidirectional sequence modeling, and why bidirectional linear attention? So bidirectional sequence modeling, as we said, like it's because many sequences around us are bidirectional. So maybe we would like to process them in their nature, which is bidirectional. But why bidirectional linear attention? So as we have seen, transformers have this capability that they can train fast. So we don't need to wait so long for the model to be trained. I mean, especially for short sequences or shorter sequences, but they are not very well efficient in inference, while SSMs are significantly more efficient in inference and linear transformers, but they can be a little bit slower to train compared to transformers. So ideally, we are looking for something that can be trained as fast as transformer, also be close in terms of performance to transformers, be as efficient as SSMs during inference if needed. So maybe you have enough resources that you actually don't want to be that efficient and you want to be very fast and use the full parallel form again, which is fine. And therefore, another third property is like that if you would like to have a chunk-wise parallel form, which means that you can have a trade-off between how parallel you want to be, how memory efficient you want to be, and basically you can have a lever that you can see in which part of this spectrum you want to move at. So ideally, we want a bidirectional form of linear transformer that can support these 3 representations, similar to their causal forms. So let's actually now give a very few recap on causal linear transformers, starting with basically the softmax transformer, which is just after extracting query key values from the input of the series of tokens, it will apply softmax attention to the tokens, and then either depending on the task, but usually not regressive task, it predicts the next token, and then so on and so forth. So the reason that we have these 2 representations was because like that in the training, you can have the full sequence and then you can parallelize over the sequence length and then actually train fast using softmax in a parallel form, in a matrix form, while in the inference, you can just use the other representation, which is just autoregressively generating the next tokens. One can see here that like basically the output of every next token depends on the whole past and in a nonlinear fashion. So basically you need to store all the past information of the tokens. As opposed to these, linear transformers were introduced by removing the softmax and just simply applying a normalization or scaling to the attention. And then they see that like you can have this parallel form of training, which is using matrix multiplications. But on the other hand, you can have an RNN, equivalent RNN to this parallel form, which you can use for inference. The significance of this is like that then you don't need to store any token. Basically, you have a hidden state like RNN that you update it over time, and then you can just predict the next token or do any task that you're working with. But there was a downfall with this specific formulation, that the performance of vanilla linear transformer was like lagging way behind the softmax variants. Therefore, there were a new area of models that they incorporated different forget gate to linear transformers. So what is a forget gate? In a very simple term, as a scalar forget gate, basically it's like that if you see this recurrence, you will add a decay term to the hidden state, previous hidden state, basically to forget how much of historical information you're carrying through the sequence. And this forget gate here, we have put it just for simplicity as a scalar, such as Mamba 2 or gated RFA. But this thing have been studied a lot, and the effect of different architecture design and different way to design this forget gate. For example, if it is diagonal, it can reach to gated linear attention. And for the case of DeltaNet, it is a dense matrix, and each of these have their own properties. in training and in inference. So it has been investigated a lot on how to shape these decays and how to build different linear transformers. Plus the full parallel form of linear transformers when are powered with forget-get, they will result in a mask which is basically a semi-separable mask. In the case for scalar, now we are just mentioning scalar just for sake of simplicity and understanding and notation. So the mask is also now input dependent, and it's just not like a simple causal mask of 0 and 1s and 0 and infinity. Basically, it can also seen as a way of decoding position of tokens in between each other. So the ones that are further from each other like pay less attention to each other, and their attention is masked with a more strong decay. Several linear models have been built upon this, which basically borrowed from DeltaNet. This is a table of several linear transformers that have been introduced after linear attention, which basically each is applying a specific individual different terms and different architecture designs. For example, as we can see, DeltaNet is applying delta rule, or Mamba2 is applying a symbol selective decay, and MLSTM is applying a selective scaling, and so on and so forth. And basically, it's a very ongoing study. Actually, there are more models that can be added to this table. For example, MesaNet is out now, mixture of memories is out, and it's really an ongoing research. So one question that one can ask is like that now that we have all these forms for causal linear transformers, can we actually have a mapping of them to bidirectional form, or how can we map them into bidirectional form, and what are the advantages and disadvantages of different mappings? And basically that's the thing that we want to investigate in this talk and in our paper. So what are the key components of bidirectional linear transformers? We would like something to have full linear attention and have an equivalent bidirectional RNN, and again have an equivalent chunkwise parallel representation, which you can decide how much of an RNN like you want to be and how much of a full parallel form you would like to be. So let's get started with the first representation, which is basically full linear attention. So for the case of full linear attention, let's first we look at full softmax attention, which, as we can see, the causal mask is gone. Basically, now we have a sequence that everything can attend to each other. And this is basically what it is used in VITs while they want to train and do the image classification task. However, like in parentheses, the positions in specific case of images is, for example, decode through learnable patches that it is added to each patch, and then you can learn the position of each patch as well. But the core of the attention block is mainly relying on softmax attention. So once now we have seen this softmax attention, one can simply remove this softmax and say we will reach the linear attention, which is actually not false. So we can have a linear attention with the form of just simple QKTV. Here we are not even considering scaling, like scaling the queries and keys. I mean, scaling the attention with respect to the rows and with respect to what it has seen from the whole keys. But, and also like this can be even further implemented such that instead of first doing the QKT multiplication, which results in attention, which is quadratic, one can first do KV multiplication, which results in a linear with the sequence length. So basically this can also be applied very efficiently. But what is a downfall of this approach? The same that was with the previous linear attentions. These are not representative enough compared to softmax transformer. So what can we see is like that maybe we can just use the same technique that was inspired by the causal form, which was input-dependent decay in resulting parallel from input-dependent mask, and then we can enhance this parametrization. And that's exactly what we are motivated by. So we can define as full linear attention as a scale. And by the way, this scale can be optional if you would like to normalize your attention, or you decide to not normalize your attention and just apply other techniques such as RMS norm to the outputs. Both are fine, but just for the sake of generality, we keep the scaling as is for now. And this scaling is just, again, scaling like softmax, but without the exponential term, scaling with respect to the keys, the whole keys of the sequence. So now that we have shaped this full linear attention, the first question is like that, okay, how to shape this mask? So in the causal form, this mask is a lower triangular semi-separable mask. Again, I'm mentioning everything for the case of scalar decay, scalar input dependent decay for get gates, just for sake of simplicity of notation and visualization, but everything can be generalized further into diagonal decays as well. So as we can see, the causal mask is a lower triangular semi-separable mask, which basically the attention mask between token I and J is masked with all the cumulatively product of all the forget case in between these two tokens. So inspired by this, we can just easily say one very way of looking at it to extend this to bidirectional form is like that have the same property for the upper triangular part of our mask as well. And that's exactly how we are shaping our bidirectional mask, which is having the exact same property as the lower triangular mask, just in the above. Meaning that every token, again, in the backward direction between token I and J, we would be having the decay of every token. The attention between these two tokens are masked with the decay of every multiplication of the decay of all the tokens in between. Or more in the mathematical form, one can look of the exact previous mask as this one on the left. If we consider that we are in a case of a non-input dependent mask, basically the forget gate is just a fixed number like RedNet type of decay, then the mask can be simplified to the middle one. And if this decay is one, which meaning that we are in a system of vanilla linear transformer, basically scale QKT times V without any M, this mask for every element is one, which basically the latter one is just basically the simple vanilla linear attention with scale. So this formulation, if we want to visualize what is happening in Y, we can see that Y is having this type of structure, which is an attention, which is basically QKT times an input dependent mask, which has the structure here is shown in a more general form, because for the case of selective mask, once we were able to shape this mask, then the fixed mask and the non-input dependent mask are also easy to shape. So this will be the output of the attention in the parallel form that we can use for training, and we can shape our full linear attention based on this. Also, in parentheses, all the light blue cells that you're seeing here are representative for causal direction, and all the yellow colors that you're seeing are representative of the anti-causal directions, or in another term, forward and backward. I will try to avoid the term backward just for sake of not getting confused with the backward path of the model. And also the diagonal terms are present in both directions, because the attention of a token on itself is always present in both directions. So this is a full parallel form of linear attention, which we constructed. So basically, we can say we have done our first component of bidirectional linear transformer, which is the full linear attention. Now we can move to the second one. Like similar to linear transformers, that they have a parallel form, which is equivalent to an RNN formulation. Here we also would like to ideally have an equivalent bidirectional RNN, which is equivalent to the full attention, which we can use for the times that our resources in terms of memory are not that high, and we cannot run full parallel form. So we would like to have an RNN that do the job. So let's dive into it and see if we can actually make this bidirectional RNN. So looking back to the attention that we have just created in the previous slide, which is just basically the normal QKT, we can actually split the upper and lower triangular parts of the attention in separate from each other. So we will be having a lower triangular part, which is exactly just representative of what is happening in the causal interactions, and the upper triangular part, which is actually mentioning what is happening in the non-causal, anti-causal direction. And as you can see here, the diagonals are presented in both causal and non-causal. So in order to have both of them having the diagonal terms, and we do not need to add another matrix to this, which is only purely diagonal, we consider that the half of the effect of an attention of token to itself is presented in the causal direction, and the other half is presented in the anti-causal direction. So now basically we have splitted our attention into two causal and anti-causal forms. Now let's look at what will happen to the mask, basically. So this is basically the mask that it is going to apply to attention in a full linear attention form. And the way we are going to split this masking to causal and anti-causal form is very much similar to how we did for the attention, which is basically a lower triangular mask and the upper triangular mask. The only difference is that here we just kept the diagonal as ones for both of them, and we did not divide this into two, just for the sake of analogy with linear transformers, that the decay of one token to itself is equal to one, basically. So because also, if you can see, the token to itself has the minimum distance of 0. So in order to not to corrupt that, we just decided to keep the diagonal as one for both forward causal part of mask and anti-causal part of mask. Even if you incorporate the same strategy as we did for the above, like attention, and incorporate the dividing by half for the diagonal, everything still works, but like the representation will be slightly different. We just keep it like this for sake of because it's easily it's more understandable, let's say. So now that we have shaped this forward and backward parts of attention, and forward and causal and anti-causal parts of attention and mask, let's take one step forward and actually put this into the full linear attention, which is above. In parentheses, for now, we are just keeping the scaling because to first establish what is happening in the regime of without scaling the attention, but everything holds, and we actually in future slides we show how to incorporate scaling as well. The analogy is very much the same. So if you just apply the full, basically split this A into the forward part and the back and the backward part, the causal part and the anti-causal parts, same if we also split the M into causal part and anti-causal part, we will reach this formulation, which basically the attention in the forward path times the backward mask, and the attention in the backward path times the forward mask. As we can see here, like the multiplication, I don't know if my cursor is visible or but anyway, like the AF, the blue A multiplied to MB, basically it consists of the diagonal terms. Multiplication, I mean Hadamard product. It only consists of the diagonal terms. Sorry, just try to, yeah, this one multiplied to this one only consists of diagonal terms, just because it's a lower triangular mask times my upper triangular mask, and everything is 0 except the diagonal. Okay, yeah. So then we can simplify this AF times MB and AB times MF to only the diagonal parts. And actually, the way that we shape this mask, M has a minus identity, which is going to create the same effect as these two, but with a negative term, which actually at the end is going to be simplified as a very clean two attention masks, one for the causal part and one for the anti-causal part. So now actually we can see that actually the left part and I mean, let's first focus on the left part. This is exactly what we see in the causal linear transformers, that this has an equivalent RNN. The other one on the right side is also exactly the same as the left one, but just in the reverse order. So you start from the end token and you try to reach the first one. So considering that, we can end up with these two recurrences with 4 for forward and backward paths. And the backward path is exactly the same as forward path, but it is just running in the reverse order. So now let's talk about what will happen to scaling. Like if you want to scale the attention, actually scaling is very much the same, because scaling is just multiplying every attention element with the summation of its diagonal. So as soon as we can have some sort of a way to sum those diagonal elements, we can split it into causal and anti-causal form. So basically the scale can be seen as a multiplication of a diagonal matrix into our attention. And then this diagonal matrix, for every element of this diagonal matrix, which is just a scalar, you can divide it into the causal path and anti-causal path. And again, we have to just make sure that when we are scaling, the scaling factor for each token is presented in both directions. So we just have to subtract the additional double counting term from each directions. Having said all of this, without a scaling, full linear attention is equivalent to this RNN, which is in both directions, these bidirectional RNNs. As you can see, the recurrence is the same as linear transformers, just it is removed with a double counting factor for the case of bidirectional form. And if we incorporated scaling, similarly, we will end up in having two recurrences. One is for calculating the actual output. The other one is for keeping track of what's happening in the scaling. And then the final output is just a summation of forward and backward divided by the summation of scaling for forward and backward. And again, we have to keep notice that we are removing these two red terms, which basically are due to double counting. So when we are going in the forward path, attention to, if you do not remove these two, we will end up with an imbalanced attention, which the attention of each element to itself, it's twice of the attention of each element to anything else. Like we are applying a mask, which the diagonal part is roughly twice all other ones. This is actually results in a very poor performance because also we are kind of corrupting the nature of the sequence. We are not allowing each token to attend to other tokens as much as it is attending to itself, if it makes sense. So in order to avoid that and have a pure, clean, full parallel form of linear attention, we have to just change our bidirectional RNN such that it is equivalent to our full linear attention, and it is a balanced attention. So now that we have established the bidirectional RNN for the full linear attention, let's actually investigate how many different choices we can make for lambda. I mean, we can make several different choices of structures of selective, non-selective, fixed, and for each of them, you can shape the selectivity in a different way. For here, we just stick to main three very general forms. One of them is lambda I being 1, which means there is no decay. The other one is lambda I being a fixed learnable lambda, which is same as ResNet style decay or a fixed decay. And the third one is just an input dependent decay. With that being said, we will just construct 3 different variants, which are basically we name them lion lead, lion D, and lioness, just to see how this selectivity and how does the choice of selectivity affects the performance and representation power in bidirectional case. Again, just in parentheses, this, however, our theorem was just like now mainly based on scalar decay, but everything is also very much extendable to the form of diagonal decay, where the lambda is basically a diagonal matrix. Just then we are not ending up with the attention times a mask, but basically the mask, since it's a diagonal vector for each token, it will be incorporated into queries and keys individually. And then you will end up with a full sequence mixing of M instead of a mask times attention. This is basically also what is lying in the core of SST and chunkwise algorithm for training linear transformers, but they do the same thing in a chunkwise fashion, such that to make sure that for each chunks, the cumulative product of decays is not over canceling or overflowing or like leading to catastrophic cancellations or leading to very, very large numbers. Therefore, they are doing it in a chunkwise form. This is a full representation of diagonal decay in full parallel form, but in bidirectional sense. In the causal form, you usually have only the left part, which is the trial, which is a lower triangular form. Okay, now just a little bit on the transformer block that this bidirectional linear attention is going to be put at. Basically, we just kept whatever the normal transformer block is, and we just replaced it with attention. And we just replaced the attention that is softmax full attention with the full linear attention. One can argue that why not adding the specific architectural designs for linear transformers such as convolution or external gating or RMS norm and so on and so forth. So basically, like for convolution and external gating, we just wanted to see how this vanilla replacement of attention with linear attention is going to end up working and how close it is in bidirectional task to softmax transformer. We know that in causal tasks, maybe the performance in specific downstream ones is lagging without convolution or gating, and these are really important. But honestly, I don't have any clue of why they should be important in bidirectional tasks, especially that, for example, convolution in a recent blog post was mentioned that it is having the connection to test time training, and that's why it will be important for causal tasks. but I personally don't see why this specific convolution could be important in bidirectional cases. And plus, we want to just see the effect of the attention. So for that sake, we just kept the block as simple as softmax transformer and just replace the attention with the linear attention block, which is basically just the attention times an input-dependent mask. And this is used specifically for training to have the training throughput of transformers. And for the inference, if we want to be memory efficient, we can just replace this attention with its equivalent bidirectional RNN form. So that being said, we will actually now reach one of the goals that I mentioned in the previous slides, that for many of these linear transformers, is there a way that we can make them bidirectional? And basically, we have provided the same theorem that actually we just discussed now applied it on many different models that are existing. Basically, everything except delta net here is using either scalar or diagonal decay. So the only thing we need to do is to make sure that these double counting terms are omitted from the bidirectional recurrence, and also make sure that the mask is structured correctly, basically based on the input, based on the type of forget gates. So then we will end up with a full linear attention for so many variants of SSMs and an equivalent bidirectional RNN for the same variants of SSMs. Specific case of delta net, it's using a full dense decay, which actually delta net itself has a parallel form. Actually mentioned in the paper that delta net, and it's also written in the paper what's the parallel form of delta net. So in that case, it's just very, very much easier also to construct the delta net's full parallel form. But another thing is like that, as mentioned, the parallel form of delta net requires inverse matrix, which would be cubic in training, if I recall correctly. So therefore, usually we would like to stick to the chunkwise form for training. Okay, cool. Now that we have mentioned, we have structured our full linear attention and the equivalent bidirectional one, let's see if we can also achieve our third representation goal, which is like a chunkwise parallel form to basically be able to see, to tune whether how much we would like to be close to attention and how much we would like to be close to RNN to balance the memory training and memory speed trade-off. So the idea is very simple. Now that we have this full linear attention of us, basically we would like to chunk each of these two separately, or see how does the chunking of each of these two is going to work out. For the attention part is actually quite simple, because here we don't have any intra-chunk or inter-chunk, sorry if I am mistaking them for each other. But basically, there is no lower triangular block here. Everything is full block. So basically, the chunkwise form of attention here, it could be constructed very easily. Like for each chunk, we just need to multiply the queries and keys of that chunk together, and then we will be having the attention for that chunk, since it's just a simple matrix multiplication. So basically, whatever we need to mainly focus in terms of chunking is how do we want to apply the chunkwise form for this mask. For the case of simple linear attention, which this mask is basically all ones, we don't even need to consider because it's just all ones. By chunking the attention on left, we have already achieved our chunkwise parallel form. But for the case of fixed decay, which means all the lambdas being equal to each other and resulting in a RedNet style mask, then we can see how we can chunk this RedNet style mask. And also for the case of input dependent forget gates, like Mamba 2, for example, as a scalar input dependent forget gate, then we basically literally need to chunk this mask. So for the case of RedNets, basically we will be having, again, for both of them, actually input dependent or no, we are dealing, in chunkwise form, we are also dealing with, depending on which part of the mask we are dealing with a different chunk. If we are in a diagonal, we are having this specific structure of diagonal being 1, and the above and below are just going to decay accordingly, and it's just repeated along the diagonal. So this will be the chunk for the diagonal masks. For the upper and lower, we are having a little bit of a different structure, but one can easily see how to shape the decay for the lower and the upper parts. Basically, they are quite the same as each other, but one of them is a scale. One of them is decaying towards let's say right corner. The other one is decaying towards the left corner. And if you basically here just exclude one lambda 4, or from here excludes one lambda 4, we can actually see how to build this mask is basically rank 1 matrix, rank 1 mask times a scalar. And you can easily chunk each part of the attention like so. The same also holds for the selective mask, but here it was a little bit of more elegancy because now you're not dealing with the fixed decays, and then you just have to consider like how is the decay basically shaping depending on which part of the mask you are. This will be very much equal to the chunkwise parallel form of GLA and Mamba 2, but just instead of one direction, you have to consider to do it in two directions, but just for the mask, not for the full linear attention, just to shape the mask based on which part of the mask you're at, which part of the sequence you're processing. And the full chunkwise form of linear attention can be shown as basically this equation, which is not like something very fancy. You start by chunking each different parts of your attention, and depending on where you are, you can basically find your attention and then find the respective output for that chunk. Same memory speed trade-offs that hold for causal sequence modeling also hold here for bidirectional case, meaning that RNN form is the most efficient one, but the slowest one in terms of speed, and full parallel form is the most speedy one, but the less memory efficient one, and the chunk version for different masks is basically trying to address this trade-off by lying in between in terms of memory and speed. Cool, so now that we have described a lot of stuff about how to apply linear attention for bidirectional sequence modeling and its equivalent representations of chunkwise and RNN, bidirectional RNN, let's see some experiments on how by simply removing the softmax in the attention and replacing it with this variant of input dependent and non-input dependent, and also simple linear attention, by just replacing the softmax attention with this, how would we perform and how will it actually work? So we have tested it on mask language modeling and image classification and on different scales. And one significant gain that applying this full linear attention gives for free is like that the training speed is way closer to transformers compared to, for example, Hydra, which is using 2 SSDs. The training speed is significantly faster. I mean, significantly, I mean twice faster. And the reason for such is that instead of stacking 2 RNNs on top of each other in different directions and apply an SSD for each, or a chunkwise parallel form for each, we would like to have ideally just one parallel form, one full parallel form, like softmax attention, and then we would build the equivalent bidirectional RNN for that. So the approach is literally reverse. So instead of having 2 RNNs and building the training for it, we will fix a training which is fast and then try to extract 2 RNNs out of it. Like the RNNs are quite similar, but just with this fraction of double counting. But the training can be done way faster since you can use the full parallel form. And the performance is actually quite close to softmax transformer and Hydra. However, still it's lagging behind slightly. And in terms of memory efficiency, we have evaluated that same as for linear transformer, the memory scales linearly. Okay, here for the bidirectional case, anyway, you need to save your whole context because the context is always available till the end. So if the context grows, your memory also grows. It's not like autoregressive text that you always want to generate. So you're not really, for example, for an SSM, you don't really care how many tokens you have already generated. Here, whatever sequence you have, you will keep it till the end. But attention will result in a quadratic computation in between, and SSM results in linear computation. That's why we are seeing that based on the context length, the memory is scaling linearly for Hydra and our Lion and RNN form, while for BERT, which is a softmax transformer, it is scaling quadratic. Same also holds for image classification task, which we had also evaluated Lion versus Vision Mamba, Vision versus VIT versus even VIT in the chunkwise form, and versus Hydra, which is a bidirectional Mamba. And then we can see that VIT is a scaling. Here it's based on image resolution, which basically means sequence length to the power of 2. So if something is scaling quadratically here, means that it is scaling linearly with sequence length, just because its image is a 2D thing, and we are just showing based on the resolution with just one of the axes here. So we have actually seen that our RNN is scaling very nice with the memory, and it's scaling linearly. And the reason that it is slightly below Hydra and Vision Mamba, we believe that it's because of the Hydra and Vision Mamba are using more external convolutions and gating and slightly more parameters. So it might be because of that there exist more computations in those. But anyway, all these sublinear models sorry, subquadratic models are scaling linearly while transformers are scaling quadratically. And in terms of accuracy and training, so ideally we would like to have high accuracy with in the fastest train as possible. So basically, what we can see here is like that Vision Mamba is having a very high accuracy, but relatively the training speed to transform is quite low. And the reason for so is like that because Vision Mamba is based on Mamba 1 and it's only relying on scans, which is significantly slower to train compared to Hydra and GLA, which are relying on chunk-wise form. And our Lion variants are being close to and even surpassing Transformer in terms of accuracy and being very close to Transformer in terms of training speeds. So Hydra is 2.5 times slower than Transformer, and our Lion variant is 1.4 times slower than Transformer. And while having a very close accuracy, ideally you would like to be in this red box on the top right corner. Also, another thing that we can really observe is that the linear variants of our model, however, even being faster than Transformer, the reason so because even in training, it's linear because you can apply KV first, multiplication P4Q. So, however, it is very fast, but it is significantly lagging in terms of performance, which actually shows that even for bidirectional sequence modeling, we need forget gates or some sort of positional information through input dependent or non-input dependent decays. And that's why linear transformer is having a very low accuracy. The other components of all the Lion variants are remaining the same. Here, the difference between the orange, blue, and green is just on the decay time. One is input dependent, the other one is non-input dependent, and the last one is no decay. And one very interesting thing that we have observed in our vision experiments is like that since image is a 2D two-dimensional input, which actually vertical and horizontal space actually matters, and you have some sort of a 2D position information, for SSMs, it's really important how you scan this image, meaning like how you flatten this patch of tokens into one sequence. And if you just flatten them normally, like how softmax transformer does, your accuracy is, I mean, it's significantly lower than if you add both representations. So in order to actually gain this positional information in 2 dimensions, considering these are like the tokens and the gridded image which we have patched, we will actually flatten the image twice in 2 different ways. One is in pure horizontal. This way, the SSM or linear transformer will understand the horizontal dependencies of the image patches. And the other one is like that we actually pass the image as vertical. And this way, it will understand the vertical position dependencies between image tokens. And we don't need to calculate query key and value for each of these representations. The only thing that we do is like that we create different masks based on each of these representations. So basically for horizontal and vertical, we will just end up with having one selective masks for horizontal distances and one for vertical distances. And what we do is just to add those 2 masks. And the query key and value for each patch is the same for both. So we just give this information of position through the selective or input dependent mask and by reordering the sequence. This actually have shown like to be very important for vision experiments that we did. Like you can really gain a lot by doing so. Like the performance is around 6%, 5% improving when just applying this simple flattening technique in different directions. So as a conclusion, we basically just focus on this study on bidirectional linear transformers, since the direction of causal linear transformers have already been studied and is an active research. We will just want to also point it out that in so many tasks that we have bidirectional linear attention, how can we actually gain from speed, memory, and chunk-wise form of this family of models? And we have built a framework that we named it Lion, just because also it's reflecting an animal like other linear transformers, that it is supporting these 3 representations. And we have also evaluated on two different tasks of mask language modeling and image classifications on different scales. And as a future directions, so as I mentioned, like one of the very key things that we have not done in this paper was like really investigating the different architectural components that can benefit bidirectional sequence modeling, such as maybe short-range convolutions on queries and keys, or external gating, or replacing the RMS norm and the scaling of the attention for each of different tasks. We have done ablations on small scale data set, but like really the effect of each of these components in the very big tasks, it's a very nice direction for future studies. And also some other real world tasks such as DNA modeling, diffusion language models, and so on are also very nice applications for future. Plus, one thing that I really maybe like it myself is like how does these masks in bidirectional term can represent different position embeddings, or what, because for example, the decay of linear transformer is recently being used as a position embedding for softmax transformers such as Path or Fox. One can also argue that how can these input dependent two-dimensional decays benefit softmax transformers in vision tasks or in bidirectional tasks such as DNA modeling and so on. So these are, I guess, some of the nice future directions that one can foresee after this study. And at last, I really want to thank all my co-authors and friends who really helped me to build this paper. And yeah, basically that's it. And thanks for having me here. And I'm available for any further questions and would be happy to discuss.
Great. Thanks for the very nice presentation. While the audience are thinking about questions, maybe I can have one quick question. So earlier I feel like in the first half of the presentation, you mentioned the fact how do you think about sort of the gating terms for the upper triangular parts. But how would you think about this when things are not? Well, you think about the gating terms are scalars for the moment. But what about things like, what about the gating terms, things like, delta net, for example, these are gating terms are matrices, and they're not necessarily invertible. How would you handle that kind of cases?
So basically, the main thing that we focused on here was scalar and diagonal. And for the specific case of delta nets, if I recall correctly, I mean, you can correct me if I'm wrong, that like in the full parallel form, you would require an inverse of a matrix.
Yes, to extend to the upper triangular version.
Yeah, which could be very costly for full parallel form. Therefore, you would need a chunk-wise parallel form. So actually, as we shown here, you indeed can have a bidirectional delta net in full parallel form, which is very similar to its causal form, but just with two different matrices T's, one for the causal and for anti-causal directions. But just training it using that would be very slow, I believe, just because that the calculating T is quadratic. It's not like you cannot have it. It will like be that, actually, also we have the theorem for it on how to do it, which is very similar to what we did here for other models. But just I would not assume it will be very fast in training. Maybe potentially also it could result in a little bit instability.
Yeah, I think that's okay. So basically, for now, the implicit assumption is now things are easy to invert, or like things are easy to define in the upper triangular version.
Things are, what do you mean by easy?
Oh, I just mean for now, the implicit assumption is that the upper triangular terms are easy to define. Maybe things like scalars or diagonal, which are easily invertible. That's kind of the implicit assumption so far.
This is implicit assumption for having the full linear attention form.
That's true. Yeah.
Yeah, but the chunk-wise form and RNN form are always there. Like this doesn't need any specific assumption because the chunk-wise form, depending on your chunk size, you will be stable, and the RNN form is always stable. So if you would like to have a full linear attention form, you just have to make sure. Same is also holding for Hydra as well. Even for scalar decays, when you are multiplying bunch of scalar decays to each other, if your decay is like very sharp and like literally after 3 times multiplication, you end up being 0, even for that case, full linear attention might not be very useful because just after 3 multiplications for each part of your mask, you will end up in catastrophic cancellation everywhere. So there maybe also you are forced to do in the chunk-wise form.
I see. Okay, that's good to know. Thanks. Okay, I don't don't see
Yeah.
questions. Do we have questions from the chat? Okay, well, if we don't have more questions, maybe we can end here. Well, maybe I can just ask one more questions. Basically think about like where do you think the field is moving? So maybe it's like completely random. And there's been like things people are trying to go beyond like quadratic attention, like it is like simplex 2, whatever those kind of things are going beyond like cubic attentions. I don't know what are the thoughts on this kind of directions.
On the cubic attention.
Yeah, or if it's completely OOD for you, we just we
No.
don't worry about this. I'm just like random questions on my mind right now.
Yeah, I mean, see, like basically what I was trying to do is to motivate subquadratic attention, and you're asking what is your intuition of the cubic attention.
Yeah,
So,
or
I mean, like very short, probably that unless it's not way much more representable than attention or linear models, I'm not sure if it really benefits to be even above quadratic. Like, I mean, already in so many applications that like you might not need specifically, for example, recall intensive tasks. I believe linear transformers and Mamba and GLA and DeltaNet can be a very good alternative to transformers. And as we can see, like people are trying to apply them in a hybrid forms to get rid of this quadraticity a little bit. So, but yeah, those are all very nice directions. I mean, I'm not very familiar with how to implement them in an efficient form, simplex attention to simplex attention and so on. But unless they are not very representative, it's a little bit, for me, it's a little bit, I prefer subquadratic models.
okay, that's great. All right, I think I don't see more questions. So maybe thanks to speak it again.
And I guess there was one hand raising up in the chat,
Oh, really? Okay,
I guess so. I thought I spotted one.
Yeah. Yeah. Well, I think either way, if people have questions, I'm sure they can. I'm sure you have your contact
Yes,
information should be
yes.
online, so people can. I'm sure
Yes,
you're
yes,
happy
it's
for
good.
people to email you for questions. So with that, I think we're just right on time. Again, thanks again for spending time, and hopefully you have a good rest of your evening. I guess it's now 8 p.m.
Thanks. Yeah, it's now 8 p.m. here. Yeah, and thanks for organizing the talk and letting me speak.
All right. Thanks.
Thank you. Bye.
Bye.